Welcome to another lesson from Transparent Physics. This one is about Newton's universal law of gravitation and his amazing friends, variations of this equation that we'll be seeing on and off throughout our introductory physics career, talking about gravity and orbits. So, Newton's universal law of gravitation. Now, what we call Newton's universal law of gravitation isn't really what he called his law of gravitation. Basically, back in the day, he was aware through other people's research and his sort of consolidation of those ideas that the amount of force between any two bodies was proportional to the product of their two masses and proportional to the inverse square of the displacement between the centers of those two masses. So we have M1, M2, a distance between them. And now his relationship, important thing to note, in the universal sense, he didn't care where these objects were. He felt that two objects on Earth, or one object in space and one object on Earth, or two objects in space, they all followed the same laws. Now this was important because a lot of people felt that the rules on Earth were different than the rules in the heavens. But Newton says, hey, it doesn't matter where you are, this is always going to be the same. Any two masses are going to attract each other proportionally to the product of their masses and proportional to the inverse square of the separation of their centers. And that was pretty much the best he could do. Now, again, that was not a small task, but he wasn't able to say exactly what that force was because we didn't have enough information about the the planets and the objects in our solar system to say exactly how that would work. Now, in a topic that I'm hopefully going to reserve for another video, there was a scientist named Henry Cavendish, and he was able to find the exact relationship between these. Now, when we take that proportionality out, we can substitute in an exact value here called big G. Big G is the, I guess there's probably that written down here. This is what's called the universal gravitational constant. And it's pretty much exactly what it sounds like. It's universal, it's about gravitation, and it's a constant. So, and this is 6.67 10 to the negative 11th. Sometimes you see it written as meters cubed over kilograms second squared. More often, at least in introductory physics for sure, you'll see it as newtons meter squared per kilogram squared. And newtons meter squared per kilogram squared is the version that I'll probably be using more often than not here. And basically what this does is it gives us a scaling factor. So we still have the product of the masses, it's still over the inverse square of the distance between them, but now we can solve for the exact amount of force. Again, this was not around when Newton was there, but subsequent research and additional information allows us to get a more specific value, not just a relative relationship, but an exact numerical amount. Now, for most of the situations we're going to be dealing with, we're going to have a sort of a special case, well, not a special case, but where instead of just having two sort of generic masses, as the top picture suggests, I have found when I teach this material that the fewer subscripts I find the better. Those sometimes get dropped and lost and switched around. So a lot of times we have a situation where we have a large mass and a smaller mass. Now this could be a planet and its moon. This could be the sun and a planet. Doesn't really matter. I just usually consider capital M to be the larger object and lowercase m to be the smaller object, the less massive object. So if I rewrite Newton's universal law of gravitation again, what I do is instead of M1 and M2, I replace that by big M and little m. And since these objects are orbiting around, we generally consider them to be basically a circular path, and r would be the radius of orbit, just easiest enough. So you can use d, you can use R. You know, as you take your courses, you might see it written one way or the other. It doesn't matter. Those mean the same thing. I will tend to use the convention R. Again, these equations are identical. They are not different equations. They are just cosmetically different. There's different skins, if you will, for the same equation. Okay, and those are both Newton's universal law of gravitation, sometimes affectionately referred to as nulg. Although I might be the first person to do that. So here's to nulg. So this equation is pretty important, and we will use it in a couple different ways because it is the origin of a lot of the other equations that we're going to be using throughout the rest of the unit, dealing with planets and satellites and things orbiting. So what I want to do is show you some different equations you can derive from this equation and other equations we've seen before, specifically within the realm of either gravity in general, the weight equation, or centripetal force equations. And we'll see where they end up. By the time we're done, we will have a lot of equations to take a look at. Okay. So we're going to switch over here. And so what we have now, let me bring it back into focus. There it is. All right. We're going to start all of these relationships with the base equation. F equals big G, universal gravitational constant, big M, the orbited object, little m, the orbiting object, and then r squared, the distance between their centers. That's an important thing to remember. Sometimes the distances are big enough that, you know, including the center or not including the center is super small compared to the overall distances. But sometimes it's very important, especially objects orbiting the Earth. We take it from the center of the Earth, not the surface of the Earth. So if you're only treating it as the height above the Earth's surface, you'll get the wrong answer. So make sure you always take it center to center here. Okay, so let's compare a couple different variations of this. We'll start it a couple of different ways. And let's go for here first. All right, so let's start to begin with this guy. In fact, here, we'll switch this over. Got a lot of paper today. All right, so we're going to start with Newton's universal law of gravitation. Now for F, first we're going to replace it by this equation. Now this equation may look familiar if you've already studied circular motion. This is an equation for centripetal force, defined in terms of radius and period. This term here is centripetal acceleration, 4 pi squared r over t squared. So this is really just F equals ma, and this is a, defined in terms of period. That's all. But we're going to substitute that in. There's going to be a little bit of mathematical juggling going on here, but let's take a look here. A little algebraic manipulation. So if we plug that value in on the left-hand side, so this is what used to be F, and then this is the rest of Newton's universal law of gravitation. Now, what I did here is I just took everything in the denominator, multiplied it through, so we didn't have any denominators left, and then I want to get t squared by itself, so I divide both sides by big G, big M over little m. Okay? And then t squared is by itself. I'm going to flip t to the left-hand side. By default, I always put my sort of the lonely variable on the left side by itself. And when we're done, we are left with this relationship. Now this relationship is what's known as Newton's version of Kepler's third law. When we take a look at this equation, we can see a couple of familiar ideas in terms of a square of the period and a cube of the radius. That's significant because when we think about Kepler's third law, if we wrote it in a different way, showed us a relationship between the square of the period and the cube of the radius. And for any object orbiting a central mass, that would be equal to a constant. Now, we didn't say what that constant was. It was just scaled with respect to all the other objects orbiting the center. So we can see that if we take r cubed and divide it to the other side, we've got that constant, 4 pi squared over big G times big M. And that value here is going to be the same for all objects orbiting a central mass. So this relationship that Kepler discovered, where there's a relationship between the ratio of the square of the periods and the cube of the average distances, can also be found through Newton's version of Kepler's third law. Why would we use this equation instead? Well, this, if you notice, in the process of carrying this derivation out, we lost little m. So if for some reason you don't know or don't need to know the mass of your satellite, now again, that could be a moon orbiting the planet, that could be a planet orbiting the sun, whatever the orbiting object is, that mass doesn't show up here anymore. So we don't need it. We're not given it. So we can look, and also that means that we're also sort of just focusing on a one-body system. Well, two bodies technically, because it's the central mass and the mass orbiting it, but we don't need to compare two objects orbiting a central mass, which was sort of one of the defining characteristics of Kepler's third law. So this scales us down to a single planet orbiting a single star, or a single moon orbiting a single star. Now this equation, I prefer this version of it. This is flexible. It allows us to go in any direction. Although you will see some resources deriving this equation one step further and taking the square of both sides and giving us this. This is known as the orbital period equation, which tells you a satellite orbiting a central mass at a certain distance from its center and a central mass of m. This tells you how long it's going to take to complete one orbit. There is a certain orbital period that will be stable for that arrangement. And we're going to talk a little bit more about that when we get to like orbital weightlessness in a later topic. Important to note here that we have slipped back into our regular requirements. This period is going to be defined in terms of seconds. So we did have a little break from this all with Kepler's third law. No longer. We can't be willy-nilly about our units. This has to be SI units, and it's going to come out in terms of seconds. So don't forget that when you're doing that calculation. So we've got Newton's version of Kepler's third law and the orbital period equation. Again, I really hesitate to call these two different equations because you can see they're directly related to each other. You just take the square root of both sides. But it is what it is. Just remember, if you're only given one of these, obviously you can then derive the other one. Probably easier starting from here going down. Okay, so that's what happens if you take NULG, Newton's universal law of gravitation, and you plug in the m 4 pi squared r over t squared. Now that's not the only thing you can do. Let's instead imagine that we're going to plug in the other circular motion equation. So instead of centripetal acceleration, instead of plugging in m 4 pi squared r over t squared, how about we plug m v squared over r? That is another variation of our centripetal force equation, where in this case now a is v squared over r. But let's follow it through, see what happens. So again, we're going to replace f by that term. So now we have, let's center that up a little bit for our sake of argument. Okay, so now we're going to have this relationship. This is just f being swapped out for mv squared over r. And this one I'm going to manipulate for v. So I'm going to take m, divide it over. I'm going to take r, multiply it over. M's are going to cancel out. R's are going to partially cancel out. And so I can see basically we take m over r and it becomes r over m. You can see r is going to cancel out with one of the r's, m is going to totally cancel out with each other, and we are left with this relationship, which is v squared big G big M over r. Generally speaking, when this is written, we take v and we take the square root of both sides. So we are left with this guy over here. And this guy is known as the orbital speed equation. I might slip up and call it orbital velocity now and again, but it should officially be called orbital speed. And this tells us in a similar genre to the orbital, let's see if I can get these on the same So we have the orbital speed equation and the orbital period equation. I don't know if I can get them all at the same time, but the idea is that for a given mass and radius, this is going to tell you how fast your satellite needs to be traveling. This is non-negotiable. For a given mass of an orbited object at a given radius, there is one orbital speed that's going to keep you stable. Any faster than that, and you move further out. Any slower than that, and you move further in. Same thing here. For a given mass and a given radius, there's a certain orbital period that's going to be stable. And if you run off that, you're either going to go further away or closer to the object. So orbital speed and orbital period often sort of double up together. These are very common to use when we're analyzing satellites. All right. And then a little shift of pace here. Let's, instead of plugging in one of our centripetal force equations, what if we just think about the idea that, hey, Newton's universal law of gravitation is an expression for gravity. And earlier in the year in physics, we had an expression for gravity. Specifically, the weight is the force due to gravity. So when we're talking about the force due to gravity, we're effectively talking about the weight. And weight is equal to mg. We'll go little m and g. We're interested in the mass of the smaller object times the acceleration due to gravity. Now that's, on Earth, it's a very specific value, but it doesn't need to be a specific value. And again, even on Earth, it doesn't need to be the same value, because you can get further away. As you get further away from the Earth, that value is going to change. So let's plug in and see what happens here. So in this case, instead of the, making sure we're in focus here. Okay. Instead of F, we write it as mg. And the deal is that you got a little m on this side and a little m on this side, so those cancel out. And we're left with this relationship. And I don't really know that there is a name for this relationship. I'm going to call it the little g anywhere equation. And the little g anywhere equation is an expression that's going to tell us the value of the acceleration anywhere. It doesn't matter. Now again, that could be little g on Earth. If you get further away from the Earth's surface, that could be little g on the moon. It could be little g on an asteroid somewhere. Technically, you could find the gravitational acceleration of yourself if you curl into a tiny ball. Regardless, we're used to g working out to be 9.8 meters per second squared, but that's for a general average value on Earth. Now, again, if we plug in the default values for Earth for its mass and radius, we'll end up with the g that we would expect to see. But this is kind of a fun equation because it lets you sort of do a what if. What would g be like on the moon? What would g be like, on this or that? So, good times, good times. So, a bunch of equations. Let's see the whole gang lined up here together. Just as a summary. And there is a whole bunch of math going on here. All right. So, we gotta leave it up a little further. I don't know if that's too small. I'll zoom in a little bit more, and we'll do a group shot later. Okay. So to review. Okay. Newton's universal law of gravitation, again, written in terms of a larger mass and a smaller mass, sort of an orbital mechanics version of it, I would say. We can take this equation, plugging in other values. We can end up with Newton's version of Keplers Third Law, aka the orbital period equation. So these equations are the same. Don't panic if you don't see both on a test, because they are the same equation. You can get the orbital period equation. You can get the orbital speed equation. And again, these tell us specific values of what we would expect to see for objects orbiting a central mass. And then our little g anywhere equation. Again, allowing us to solve for g when it's not 9.8. Also, for the record, that's going to not come out as a negative value. That's simply the magnitude of the acceleration. A lot of people sort of expect to see that come out as negative, but it won't in that equation. It just tells us what our magnitude is. All right. There are lots of formulas here, and therefore lots of potential problems that we could solve with these equations. I would say they are a little bit uglier equations. Working with cubes and things like that is not usually everybody's dream. And on top of that, what we see is that often when we're solving these problems out, we will get messier initial information. These values have to be given in terms of, say, meters. It has to be given in terms of kilograms. So often we're going to have very, very, very large values that we need to be plugging in. A lot of scientific notation. So you have to be very careful when you're trying to solve these out on your calculator, so you don't, you could have everything set up properly and still get a wrong answer if you plug things into your calculator incorrectly. But we'll have a video after this one showing you some samples of how to work with some of these equations. All right, a lot of math in this video. I hope you found the derivation of the formulas to be kind of useful. It's not that intimidating, really. They all sort of come from the same source, Newton's universal law of gravitation. And I appreciate you spending your time with this lesson, and I hope we've made things a little clearer with transparent physics.